It's very nice, and I'm very happy to have today with us Swetha Bhagwat from currently in Bangalore, but she's a postdoc at La Sapienza University in Rome. And we already invited her to come visit us physically when it is possible and when she's back in Europe.
Thank you.
Swetha collaborated with me back when she was in the LIGO Scientific Collaboration, and even afterwards when we were both very close to each other in upstate New York. We work on very similar things, so if anyone is interested in things that she talks about today, we do have projects on these topics which we would like to work on. And of course, I'm sure Swetha would also like to collaborate if possible. Yeah. And she's also a very nice person.
Thank you.
Which I don't say about most of our speakers. But she is exceptionally also a nice person.
Thank you.
So let's hear about merger ring-down consistency, tests of strong gravity using deep learning.
Okay. So I'm going to talk to you about the merger ring-down consistency. It's a new test that we're proposing to test strong gravity, and we try to use deep learning algorithms to do it. So this work is right out of the oven in sense that it came on arXiv like today morning. So it's really, you guys are the first people hearing it. So do let me know what you think at the end of it. And you can interrupt me whenever you want. All right. First of all, just a brief motivation on why testing gravity. So even though gravity is the oldest known force, there are regimes of gravity that are not tested thoroughly yet. So general theory of relativity is the current state of our description of gravity, but its ubiquitous validity is sort of questionable. There are very interesting regimes like the cosmological length scale, strong field regime, nonlinear dynamics, the black hole horizon scale physics, and quantum length scale physics that still needs to be probed and understood better. So testing gravity with experiments and observations are very important at this point. And gravitational waves coming from compact binary merger allows us to probe gravity at some of these interesting regimes and allow us to do some really powerful tests of gravity and Einstein's theory of relativity. So, wait, do you guys see the panel with people as well?
I see the illustration.
Okay, perfect. All right. So the binary black hole coalescence can roughly be broken up into 3 different regions. There is the in-spiral region where you have 2 black holes that are separated from each other far enough that you can assume that these black holes are moving towards the center of mass and quasi-circular orbit. So this region generally is weak. The dynamics of the gravity in this regime is mostly weak field gravity and can be explained as Newtonian gravity plus some corrections. So this region is what we call as the post-Newtonian evolution. Then after a point, what happens is these black holes come close enough that you can no longer explain it as quasi-circular evolution. They ram into each other in a phase that we call as plunge, and they merge. And when they merge, they'll form a distorted black hole. And this distorted black hole then rings down and dissipates more energy in form of gravitational wave, and finally settle into a stable state, which we call as the remnant black hole. So this last phase is what we call as the ring down. All right. So what we see here is in this entire evolution, you've got different physics that is happening at different scales and in different regimes of gravity. Like in the beginning, when you're in the spiral phase, you're looking at rather weak gravity with black holes moving fast, but not super fast. As in, like, you have relativistic correction that you have to add in, but you can still work with them as corrections to Newtonian gravity description. So you have this large scale, uh, okay, not large in sense of cosmological scale, but large-ish scale dynamics going on. Then when you're coming closer towards the merger plunge regime, you now have a very interesting physics that goes on in the source frame, which is that it's seeing both strong field and nonlinear evolution of the system. And this is very interesting because this is one of the few places where you actually see the nonlinear part of Einstein's theory actually showing up. And then the last one is again the strong field gravity, and you're again probing something around a horizon scale. But now this part is explainable via the linear perturbation theory. So you're essentially probing three very different but all interesting regimes of gravity. So, all right. So, one of the very popular tests that LIGO does is something called as the in-spiral merger ring-down consistency test. So, what you try to do is you try to look at the signal and see that do all of these regions or do all of these regimes of gravity sort of behave as they have to behave. So, essentially, you look at the entire waveform and you see it has the evolution uh, roughly and globally followed what Einstein's theory of relativity predicts, right? And the way we do this is in the following way. So we look at the final mass of the remnant black hole form, the black hole that's formed after the two black holes merge. We try to measure the mass and spin of this remnant black hole by two independent methods. The first method would be like you look, so you essentially take the waveform, which is in the bottom panel. You you cut the waveform into two parts, one which is pre-merger and another which is post-merger. Take the pre-merger waveform independently and estimate the initial binary parameters, which will be your mass ratio, the ratio between the mass of the smaller and the bigger black hole that are coalescing, um, and the spins of these 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 binary black holes. And then you run a GR evolution, typically through a numerical simulation, and then you see what is the remnant that you expect such a system to form. So so you take the measurement of initial binary parameters and then you estimate what the remnant black hole should be. And the second independent way of assessing or estimating the mass and spin of the remnant black hole is to look at the post-merger part of the waveform. So you look at the frequency and the damping of the ring down, the very end of the black hole, binary black hole evolution. And these contain information about the properties of the remnant. So if you can measure the frequency and damping in the very end of the waveform, you can actually reconstruct the essentially you can estimate the mass and spin of the mass and spin of the remnant black hole, and then you compare these two and see if they agree or not with each other. If GR is a valid theory, then the spin and the mass of the black hole computed by both of these methods should agree with each other. So this was a test that was done with yeah, this is a test that's done with all of the um, events that LIGO detects. But on this slide, I show you what we had done for GW15 or 914, the very first gravitational wave detection. So the waveform was taken, and heuristically, we cut the waveform, cut the entire binary black hole waveform, which is shown on the left panel. Where you see the red line, that's where you separate the pre-merger and the post-merger part. It happens to be 132 hertz. It's not a special frequency. They just decided they wanted to do it at that point. So you cut the waveform there. You use the pre-merger and you compute what should be the final mass and final spin of the remnant. Then you take the post-merger part. So you see a ring down, which looks like a damped sinusoid. You take that, you measure the frequency and damping time and convert that to find what's the final mass and final spin of the remnant. Compare those two. So on the right panel, you see the comparison and you see whether or not they match. So on the right panel, on the x-axis, you have the final mass of the remnant. On the y-axis, you have the final spin. And unfortunately, both of them are blue, but the darker blue that has been labeled as in spiral is the the region where you have 90% confidence interval support for the final mass and final spin. So that's the region that the inspiral predicts the final mass and final spin of the remnant should be. And the elongated, slightly lighter purple color that's been labeled as post-inspiral is the measurement of final spin and final mass that you expect when you do the analysis using the post-merger part. And the dark black tiny region is the place where you see both of them are consistent. So as long as you have a patch that that overlaps the post-merger estimation and inspiral estimation, then your signal is consistent with GR. All right.
The black is the full estimation with the full waveform, right? You don't get it as from cutting both of the blue or purple curves. It's just full analysis.
It's the full analysis. The region of overlap between the dark purple and light purple is where you have the intersection between what the pre-merger computes and what the post-merger computes, right? Yes, and that is consistent with the whole waveform calculation of the whole waveform. So, all right. So this was the result that was published by the LIGO collaboration a while back. Okay. So then now the thing that we were interested in is the fact that when you do this, sorry, I'm going to go back. When you do this computation of final mass and final spin from the inspiral, from the pre-merger part, what happens is that you try to estimate the initial binary parameters. Now, the inspiral part of the waveform is long and typically contains a lot more cycles than the plunge merger phase. And the plunge merger phase is the one that actually contains a lot of beautiful non-trivial predictions of GR because it sees both strong field and non-linearity in them. But because it is so small, most of the parameter estimation does not see that part very well. So essentially what happens is that because it's short, okay, so in this slide, I've taken a table from Arun et al. 2005, and there's a box that I have, what do you say? I have boxed a blue thing at the very end of the table where you can see that, so generally the PN waveform is what we call as the inspiral. And you see that the uncertainty in measurement of the chirp mass and eta, so you can think of them as proxies for total mass and mass ratio. They're quite good even if you don't include the merger at all. So you see that it's not very sensitive to the merger. The parameter estimation of the initial binary parameters are not very sensitive to the merger phase, which also means that your IMR test itself will not be very sensitive to the morphologies of the ringdown. So you can have few percent difference in the merger and you still may not be able to figure it out given that there's going to be statistical noise, etc. on the waveform. So one of the things that
which is this, what's taken as the cutoff frequency for this 2005 analysis?
I think they've gone up to 3 PN with, I think, the frequency cutoff at ISCO. I don't remember what's exactly the system.
So for 150914, ISCO was considerably lower than 132 hertz, right? It was something like 70 or 80.
Yes, I think it was 82 or something. Yeah.
So shouldn't we have seen something very, very sharp in the previous slide for the pre-merger part? Or do they append some of the merger to the inspiral? Do they take some of the inspiral and move it over to the merger? Or
so wait. So here you mean sharper as in the contour should be sharper?
I don't remember. Yeah, I don't remember the ISCO frequency, but the next slide shows an uncertainty of about 5 or 6%
Wait, 1 second. Sorry, I should have been more clear with this. So I mean, so these numbers quoted are the uncertainty with respect to the full IMR waveform. So if you have an IM, so this is completely without the noise. This is just a simulation. I mean, they take literally the post-Newtonian waveform and they compare it to a full IMR waveform, and they see that if you just have a 1 PN waveform, then you can estimate, for instance, for a double neutron star system, you can estimate, so the error in estimation of the chirp mass is going to be 0.027%. Error in estimation compared to a full IMR. So this one does not have a noise. This one does not. It's just a waveform. So in this study, what they do is they're just trying to calibrate the waveform and figure out how much further you need to go into the post-Newtonian. So this is a very theoretical computation, and it does not really.
No noise.
Yeah.
There's no noise here. Okay, got it.
Yeah. Okay. So I mean, the only reason I wanted to show you this was to say that a 3PN waveform already does a very good job at estimating the initial binary parameters. And so it sort of is an indication that even in the absence of merger, you do get a very good parameter estimation for chirp mass and eta, symmetric mass ratio. All right. So I go to the next slide. So what we wanted to do is we wanted to sort of tweak the IMR test so that it becomes more sensitive to the plunge merger morphology. So this was the aim of it. And we also sort of wanted to combine information across multiple ring down observations, somewhat like stacking, but not in the sense that we're trying to extract the frequency and damping time, but we want to do an IMR consistency by combining information. So this was the sort of the goal of it. And more physically, what we wanted to try to do is we wanted to check if the perturbation condition that is set during the plunge merger phase sort of was an agreement with the mass and spin of the remnant that is formed via a GR evolution. So that was the goal of this work. So let's first take a slightly more closer look at the ring down waveforms. So the ring down part of the binary black hole evolution is a part that can be explained or described as the evolution of perturbation on the metric of the final remnant black hole that's formed. So the gravitational wave that's associated to this part at asymptotic infinity, you can explain that as linear superposition of damped sinusoids, where the damping and the frequency of the sinusoids are characteristic to the black hole. So the spectrum of, they're discrete, and the spectrum of these frequency and damping time is what we call as the quasi-normal mode of the black hole. So these frequencies are very are unique to the mass and spin of the black hole. Okay, so the frequency and damping time, in turn you can invert them to find out what is the mass and spin of the black hole. On the other hand, which of these modes, okay, one more thing, the L and M index over here are very similar to the quantum indices, as in they sort of mark your angular modes. Okay, and then next you see ALM and phi LM, which is like amplitude in the phase of these damped sinusoids. And these sort of have imprints on the perturbation condition. So which mode gets excited in the ring down depends on what conditions are set during the plunge merger during the evolution. So these sort of contain information about the symmetries during the merger. Okay, so the next slide. So what can be done is you can express the frequency and damping time in terms of the final mass and final spin of the black hole. And you can express the amplitude ratio of different modes in the ring down, which we call as quasi-normal modes, and the phase differences in terms of the initial binary parameters. So if you take a non-spinning binary system, these can be expressed in terms of the mass ratio, the ratio of mass between the smaller binary and the larger binary. So then you can sort of express your ring down waveform as a time series that depends upon three parameters: the final mass of the black hole, the final spin of the black hole, and the mass ratio of the initial binary system. Okay. Then, so now what happens is, so also because the ring down is short, it just has a fraction of SNR compared to the entire in spiral merger ring down signal. So what we try to do is we statistically combine information from multiple ring downs, like I just said before. Then what we demand is that all of the observation of ring downs have to statistically satisfy the test that we are going to propose very soon. And we demonstrate a proof of concept study for this, for the working of this test, using simulated ring downs embedded in Einstein telescope like noise. So Einstein telescope is a next generation ground-based detector. Okay.
Can you go back to the one slide further?
Yeah.
So you have here three parameters: the total final mass, final spin, and the initial mass ratio Q. But you say the black holes are non-spinning.
Yes.
Doesn't that mean that you're actually redundant here? You only need two parameters?
Exactly. I'm going to come to that. I'm literally going to use that exact same concept that you just came up with. I mean, the whole test is really based on that. I will be back to that in 3 slides.
Okay.
Yeah. Okay. So, so now that we decided that we wanted to do statistical number of combine information from statistical number of ring down, we had to do a large number of parameter estimation. And the easiest way to do them, or like not the easiest, at least the quickest way to do them is to sort of employ deep learning algorithm where you sort of train your machine once and then it does the parameter estimation quickly. Okay, so what we try to do is we use this neural network architecture called conditional variation autoencoder, which is sort of a setup that's commonly used to replace Bayesian parameter estimation. So we use that setup. So what we do is we generate 10 power 5 ring downs in Einstein telescope like noise. And we use 90% of this, 90% of 10 power 5 simulated waveforms to sort of train the machine, to tell it about, essentially to teach it how to extract the parameters out of the ring down. And then we use 10% to sort of validate, to actually check whether or not it's able to do it. So this entire training process takes about 84 minutes on a single GPU. And then what we do is then we simulate 10 power 3 ring downs and we perform a proof of concept study with this 10 power 3 ring down. So we assume that whatever the next generation detector is, Einstein telescope at some point has this detected 10 power 3 simulated ring downs, and we sort of try to combine information from all of these. So the PE in this framework is super quick. It takes 40 milliseconds to do the parameter estimation of one waveform, and we see that all of these posteriors agree with the PP test. So the confidence interval is as it should be in a Bayesian sense. Okay, so this was the slide.
And all of these waveforms are non-spinning.
All of these waveforms are non-spinning ring down only waveforms. All right. So just to give you an illustration, so we take in the, how do you say, right bottom panel, yes. In the right bottom panel, you have a ring down signal injected into the Einstein telescope like noise at an SNR of 60. And on the left, you have the parameter estimation done via this CVAE neural network. So on the diagonal you see the final mass, the spin of the remnant, and the mass ratio. The dashed vertical lines, black lines, are the 90% confidence interval, and the blue lines are the injected true values. So you see that the posteriors are consistent. I mean, in fact, they recover the injected value quite well. All right, so this was just to show that the parameter estimation does work quite well with machine learning setup. Okay, then we go to the heart of the concept of what we are going to propose for the merger ring down consistency test. So again, we have now we rely on the measurement of remnant black hole spin via two different methods. The first method would be the direct measurement of final mass, sorry, the direct measurement of the set of final mass, final spin, and q for each of these, for each of the n ring down events that we are looking at. So for 10 power 3 events, we do a parameter estimation and compute final mass, final spin, and the mass ratio. So we have a list of final spins. Now just like Afek just pointed out, in as long as GR is the underlying theory of gravity, these three parameters are not independent. You should be able to map the final spin and the mass ratio onto one another, because at the end of the day, both of them sort of set the symmetry of the system. The kind of essentially both of them sort of are a proxy to how much angular momentum the system is going to have when it collides, modulo the scale factor, which is the mass, total mass. So essentially, you can map it, and people have fit the numerical simulation to get analytical approximate formula uh, for the relation between the final spin and the mass ratio, which is given in this in on the slide. So what we're going to do is we're going to use the final mass and the mass ratio to compute final spin using this equation. So this will be the inferred spin. So now we have two different measurements of the spin, one that is directly measured via a PE, and one where we take the measurement of final mass and Q and sort of invert it to get the final spin. So now what we ask in this consistency test is that these two measurements should be consistent with each other. All right. So this is the main plot um, of the paper. So what we do is we generate 10 power 3 ring downs in the range of 40 to 80 SNR. Uh, we plot we plot the measured spin versus the inferred spin, and we try to pass a line which demands that the measured spin should be equal to the inferred spin. So, and then what we try to do is we sort of write this formula where we say that the measured spin is equal to a plus b times the inferred spin, and we try to fit for a and b. So if GR is the right theory of gravity, then you should see that the best fit for A should be 0, and the best fit for B should be 1. So essentially, literally, it should come out that the measured spin and the inferred spin are equal. We see that these scatters are very close. I mean, it does follow this, and you do get A and B very close to what they should be in GR for these 10 power 3 signals. You see all of these points are scattered around this line as expected. So it does seem that you can do this test reasonably well. The next thing we ask is, do we really require 10 power 3 signals to do it? How does the uncertainty on the fit for A and B depend on the number of signals? So that's what is the next slide that we'll see. So we are going to see how this change. So these are so on the x-axis you have the number of observations. So where you see 10 power 2, that means that you're seeing the best fit parameter A and B when you have 100 signals. So and how do you say this? The diamond shaped dots are the points where you are the estimation of A and B. So the A is the one with orange color, B is the one with blue color, and the bands are the uncertainty in the fitting for A and B. You see, first of all, you see that all of them converge with both of them converge with the number of observations. Both of them are the mean value of them are consistent with GR. So A is around 0, B is around 1. And we see that there's a power law convergence with number of observation and the uncertainty in the estimation of A and B, which is sort of how well you can do this test. or how well you can constrain GR, has a power law convergence given by the formula at the end of the table. So it goes as 1 over root n, as we expect. So this is my last slide, actually. So we have demonstrated a proof of concept study for a new test of GR. We've also illustrated that we can do Bayesian deep learning methods to infer the posterior parameters and conduct precision tests of GR. And one thing I do want to emphasize is that we are not saying this is better than the IMR test or this has to replace the IMR test, because this is trying to probe something that is slightly different from an IMR test, from a standard IMR test. We're proposing that there should be another test that we should do along with the IMR test, along with the standard IMR test, because it's just another set of information that you get out of them. Some of the extensions that we're thinking of doing is to include spins. So in this situation, it will be slightly more complicated, because now we are going to have the dependence on both the mass ratio and the initial spins when you're trying to calculate the final remnant spin, but it's still doable because none of our formalism actually requires us to have an analytical closed form relationship. So that's something that we are going to extend this work to. And another thing that we want to do is we want to include supermassive black holes in this study. That's it. That's it from me.
Okay, before I ask more of my own questions, let's open the floor for student questions. Students and postdocs, for that matter. Any questions, anyone?
Yeah, so what are the advantages of this method as opposed to the IMR test? Is it's less time and computer consuming? I mean, yeah.
So, I mean, this takes an inspiration from the inspiral merger ringdown test, but it tries to do it tries to do a different thing. So it's not like they're not on the same footing. It's not right to compare an IMR test with this, because we are not claiming it's better or it's just different. We are trying to see something very different, right? We are trying to see if you can sort of find a consistency between the merger phase and the ring down phase. So in more physical terms, what we're trying to ask is that, is the perturbation condition set up during merger consistent with the ring down of the final black hole? Like, are these because these two things are not independent of each other, because all of these are set by the symmetries of the initial system. That's what we're trying to ask. Whereas the IMR test sort of checks if the waveform itself as a whole evolves, how do you say, roughly as expected by GR. So the thing is, this does not take inspiral into account, which means, of course, you're going to lose out information that comes through the dynamics that happens at an inspiral scale. But you're sort of trading off that information to become more sensitive towards the merger. Does that answer your question?
Yeah, thank you.
Okay.
Next. Okay, if not, I'll ask. Okay. So if I understand correctly, both your method 1 and method 2, which you're comparing it for consistency, they use the same data, right? They both use the same data, but one of them only estimates. Actually, they kind of both estimate 3 parameters from the same 3 parameters from the same data, but then method 2 puts a patch on the eye for one of the parameters and tries to estimate it from the other 2.
Yes, exactly. exactly.
So the question is, in that case, if they use the same data and the same parameters that are estimated, are you not really just kind of checking the consistency of the approximation formula? I'll
Yes,
put
I mean,
it another way. These are simulations, right? So you know the exact chi-f, eta, and total mass.
yes.
So can you ignore the data and run the same guessing game with your machine learning app? For a bunch of simulations, take the final mass, take the final spin, try to guess the mass ratio eta, and produce the same plots of this. I'm guessing you'll get the same convergence because.
So you are saying just do the reverse of what we did, sort of like instead of using the ring down to instead of using the mass ratio to estimate the spin, use the spin to estimate the mass ratio separately.
No, that's not what I meant. I got you wrong.
Okay.
I thought that's what you were doing. No, I'm not saying. Do the same pipeline. Use the mass ratio and the total mass to estimate the spin, but take the data out of the equation. So just use the parameters. Use the exact. Okay, for method 1 you need the data, but for method 2 use the actual fully known m and eta.
Okay.
And see what your estimation gives you based on that. If you recover the GR estimate, because it might be in that case that if you see the same convergence in that case, then it might just be the regular square root convergence of using more and more events. So the randomness cancels out, and you just get the regular convergence, but you're not actually data informed. It's just random noise, which you're sorting through.
Right. I mean, at the end of the day, if GR is right, you have to get them to be equal, right? There is no stochasticness in this. So whatever stochasticness is coming, I mean, so we are simulating GR ring downs. If we had simulated a bunch of GR mixed with non-GR ring downs, then of course you'd have found the spread. Right now, all of the stochasticness is coming through the noise. So I think what you're saying is going to happen just automatically, no? Because the spread you're seeing is literally the spread that's coming out of the noise. So somewhat like a Poisson statistic, you add more signals, you're going to reduce it by 1/n.
Right. Square root.
Yeah. Exactly. So I think we get exactly the same thing. Sort of, you see the square root of 1/n even when we do it this way, and it's pretty much exactly for the same reason that you're pointing out.
So you're saying that having a square root convergence is what tells you that it's consistent with GR.
Exactly.
And
it's one of the things that tells you that it's zero. Like, okay, so you have the fact that you have the convergence of, A and B are centered around the right value. So A and B are centered around the right value. The A and B have square root n convergence, and the fact that even when you have a small numbers, like even if you the edge of this plot has like 20 simulations. So even when you have just 20 simulations, you don't see a wrong mean. Sort of tells you that you are consistent with GR.
Okay. So if we had some deviation from GR, then we could see it by the mean values not being in the right place.
Yes.
Or with it not converging, or would it still converge with a square root to the right values, but maybe converge slower if there's some other effect that's effectively random that we don't know how to model, and so it cancels out? Would we distinguish those?
So that's the problem, right? When you're talking about an alternative theory, it depends on what modifications you're talking about, no? Like if you have a modification that's going to change for whatever reason, for whatever, I don't know what physical reason could lead to this, but say you have just changed uh, the amplitudes and of excitation, and for some really random reason you form the exact same remnant black hole, and it is a black hole. If you have a situation like this, then what's going to happen is your estimation of this entire line is going to get screwed up, right? Because in that situation you're going to estimate a wrong q. So when you're going to plug it into this equation, you're going to get a wrong spin, uh, right? So essentially, in that situation, what's going to happen is you're going to expect that your so the mean of these quantities are going to change. But on the other hand, if it turns out that there's a systematic change in such a way that it is somehow leading you to a smaller q and larger masses, then you can just have a spread that is different. So, like essentially both of the convergence as well as the mean of a and b sort of indicates what is gr, and if you find deviation in either one of them, it's a red flag that you should go chasing after.
And what do you estimate the mass spin and mass ratio based on? Does the neural network do that with the whole data? Does it only use particular modes? What kind of information does it have for you? Does it just learn it from the 100,000 examples and then go on its own?
Yeah, it just learns from 100,000 examples of two modes. Like so you have a 220 and 330 mode in it.
Mm-hmm.
We haven't put higher modes, but we can put it just because it was a proof of concept. We put two modes. Yes, so we train it over 100,000 signals, and then it just does the next one. So it learns how to pick out these parameters, and it picks it out when you give it a new signal.
Is there any way to ask how it does it, or what the network is actually calculating physically, or is that just completely locked within the neural network?
It's sort of completely locked within the neural network. So the thing is, the way it sort of does it is there are two sort of loss functions. One which okay, so essentially the way this particular neural network sort of works is that it takes in it takes in the first waveform. It sort of tries to estimate what is it sort of tries to pick out, reduce the dimensionality of this space. So essentially it'll take a bunch of ringdowns and it'll identify something. So if I were the network, I would have identified it as damping time and frequency. We don't know what that network actually picks, but it picks some smaller number of variables to sort of parameterize the signal. And then what it does is it tries to see if these things that it has picked out is really true by trying to compare it, trying to reconstruct the signal and trying to compare it with what it's been given. And it keeps tweaking it till it thinks that so then it sort of associates that, okay, if I get a mass 1 and spin 1, then this is how it looks, and I should give out the mass 1 and spin 1 sort of a thing. But what exactly happens and what it picks for the variables and stuff, this is, I think, at least at my level, it's a black box. I think you need yeah. So
how much more complex do you think it would be if you added spins?
Not very, actually. So the thing is, this relation is going to be not analytical, but none of these networks really require you to have anything analytical. Or I mean, essentially, as long as I have a table where I can have a lookup between, okay, you give me these two pairs, this corresponds to this initial mass system, it is doable. I mean, you can't use this particular neural network because this one is trained on non-spinning binaries, but yes, you can train another one where it also sees the spinning binary systems And it's very much doable. It's something that we're actually thinking of doing in near future to see if we can include spin.
Cool. Any other questions? This code is all, I mean, the package used for neural network, it's Python code, it's standard, it's available, or do you use something special?
No, these are all from this Python package called PyTorch. And we are also going to make this code public in a Git repository soonish. So yes, I mean, none of the main engines of this neural network are things that we did. Like, it's literally like packaged thing that is readily available in Python market, and you can just use it. It's a little bit of, there are parameters that you have to sit and tune. Like this one has, I think, 15 hyperparameters, so you have to like make sure that the PE actually works and stuff, because for a long time, for instance, we would get a higher spin for whatever reason. Like the parameter estimation kept giving us a higher spin, and then we had to tune a bunch of parameters to sort of get it adjusted. So that's there, but then the architecture itself, it's a very popular architecture. It exists.
Okay, great. Well, I think some of us will surely want to look at the code and see if we could play around with it.
Yeah.
Any other questions? If not, let's thank Swetha again.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you very much.
Say again that we would love to see you in person, visit here at some point.
Thank you.
Thank you for closing the semester for our Astro seminars. Good luck to everyone's exams. Good health to everyone in these days. And we'll reconvene next semester for these seminars. Good luck. Take care.
Bye.
Thank you.